let's talk about Rolle's theorem and the mean value theorem. Basic concepts here involve the ideas of secant slopes and tangent slopes. So Rolle's theorem says if the two y values of endpoints, let's say x value a and x value b, if the y values of those are the same, in this particular case you can see the y values line up, and the function is continuous and differentiable, all right, so it's smooth, there's no breaks, there's no vertical tangents, then somewhere along this smooth line there exists a tangent slope which is the exact same as the secant slope. So in this particular case, since the secant slope is 0, there's somewhere along this line there's a max or min or an extrema that there's a tangent slope exactly the same. Mean value theorem is very similar to this. It's basically a corollary, what it's called, of Rolle's theorem. And it basically says the same idea. If the graph is continuous and smooth, if it's differentiable, then if I find the secant slope, somewhere along the line there's a tangent slope that also matches that secant slope. Basic concept about the mean value theorem. So again, some C that exists in A and B. So here's A, here's B, some C in between them, such that f of C, the tangent slope, f prime of C, will match the secant slope of y minus the y over x minus the x. A couple examples. So here's a standard parabola. We're talking about the interval from 1 to 4. Find the C value guaranteed by the mean value theorem. So first of all, we find the secant slope. We know that there's no issue. This is a parabola. There's no issues with continuity. There's no issues with differentiability. This thing is continuous and smooth, not an issue. So I find the secant slope. So g of 1 is 10 and g of 4 is 40. So differences in the y's over differences in the x's gives me a secant slope of 10. This is between the two endpoints of 1 and 4. This is your average rate of change. I take the derivative, which again, straight power rule here, and I set the derivative equal to that secant slope we just found. I solve for x, and I find out that x is equal to 5 halves. Notice 5 halves does lie on this interval. So g prime of 5 halves is equal to 10, and this matches the secant slope with this specific tangent slope. So here's your point guaranteed by the mean value theorem. It's x is equal to 5 halves. This lies on the interval of 1 to 4, and the secant slope of the originals is matched by that particular tangent slope. The second one, if we take a look at this graph, we're going to check and see if Rolle's theorem applies here, okay? Because if we plug in -1, we get 0. If we plug in 1, we get 0. This is to the original function. Okay, so on the interval -1 to 1, they both give me a y value of 0. So in this case, it's Rolle's theorem because I'm looking for a horizontal tangent. However, we have an issue here. Somewhere in here, we notice that x is equal to 0 in the denominator is a non-removable discontinuity. You cannot remove it by factoring. Therefore, what we got going on here is we got a vertical asymptote going on here. This thing is not continuous then on the interval from -1 to 1. And since it's not continuous, we cannot apply any of the theorems on this. Okay, we'll do a bunch more of these problems tomorrow in class. You can take a look at the homework set that's hopefully online already and see the basic concepts. But again, basic concepts is we are trying to take and find points where the tangent slope is the same as the secant slope on these intervals. So if we've got an interval from A to B, can we find a point where the tangent slope is the same thing? So we find the secant slopes, and then we find the derivative, and we set the derivative equal to the secant slope. Basic concepts. Thanks.